So welcome to deep reinforcement learning and control. On Monday, we had started on the topic of model-based reinforcement learning. And the first setup that we visited is when we know the state as a low-dimensional representation of the environment, okay? And we said that we'll train dynamics models that given such a state and an action representation will predict the next state. If you remember last time where we had closed is on these graphs from 2017 that showed that early in training model-based methods outperform model-free, so they learn much faster. But as training time goes on, they saturate, and essentially, as training time goes on, model-free methods clearly outperform model-based methods, okay? And one trick we said to make use of model-based learning in that case is to potentially initialize our policy with model-based and then switch to and fine-tune to model-free so that we don't essentially suffer from this asymptotic, plateauing of performance. I had told you last time without actually, giving any proof or any evidence, empirical evidence, that the reason behind this is that we were not representing models uncertainty, all right? So the models are only good around the data where they were used to be trained on, and this is precisely what we'll discuss. This is the first paper, extremely simple paper, deep reinforcement learning in a handful of trials using probabilistic dynamics models that really, put the uncertainty modeling as, the most important, actor, let's say, in model-based RL. Proposed the dynamics model that models its uncertainty using neural network ensembles and applies it on established benchmark and shows that model-based reinforcement learning with this modification actually outperforms model-free methods. Okay, so now we'll see exactly what they did. Before we start on the description of their algorithm, we need to discuss two important terms, epistemic and aleatoric uncertainty. So there are two types of uncertainties in the world. One has to do with the uncertainty due to lack of data. I just haven't seen data from that type of regime of the system, and thus my model doesn't know its behavior, the system's behavior. The system's behavior is super well defined, maybe very deterministic, and it's just that I don't have data, and I was not trained and I cannot model it. So we call this epistemic uncertainty, and this is precisely the uncertainty that I've been talking about, right? So uncertainty due to lack of training data. Okay, and we need to model which parts of the state space I know and which parts I do not know. This is epistemic uncertainty. Now, aleatoric uncertainty has to do with the fact that all of us have spent tremendous amounts of time watching TV, and we're super trained on, using the remote control. Still, we cannot predict what we're going to see when we press a button, simply because the environment is very stochastic and multimodal inherently. Is that clear? It's not that we don't have data, it's just that the environment is really stochastic. Is that clear? So we call this aleatoric uncertainty. So dynamics model should be able to model both. So let's see. So aleatoric uncertainty has to do with the fact that the environment can be stochastic with the same state and action, pressing number 3 on the remote, in different time steps and be land in two different states, S prime and S double prime. And this means that our state right now just does not capture enough information to reveal to us which of those possible futures will happen. I mean, under a complete information where you know all the TV stations and what they're showing, then there's zero aleatoric uncertainty. You know everything about the world. It's just that this is impossible. It's impossible, I say, to capture all possible information in the world from microatoms to macro to microatoms, and this is what happens inside our bodies and what bacteria and what viruses are. And so which, if you knew that, then you know exactly if you're going to be ill tomorrow, for example, right? But we do not know that. Does this make sense? So we don't care if the environment is stochastic really or not. What we care is that given our state, because this is what is available to us, we cannot actually predict the future. Is that clear? Okay. Yeah, and what is stochastic under one state representation, maybe not stochastic under another. And it's exactly what I told you. If your state has all the TV program, then there's no uncertainty on what you're going to see on the TV if you press a particular button. But The truth is that we will always have part of the information hidden from the world, so stochasticity will always be there, aleatoric uncertainty will always be there, and this is something obvious things to say. There is nothing really surprising here that I'm saying. So how we're going to model that? Well, people do not worry terribly about it. This specific paper particularly does not worry. It just puts for the next state the distribution as opposed to 1 point estimate, a Gaussian distribution specifically, even single mode, right? I would say this is really not worrying about multimodality of the problem. And that Gaussian distribution specifically, they don't parameterize only the mean vector, okay? And it's a multivariate Gaussian distribution with one dimension for every coordinate of the state, but they also parameterize the covariance matrix, okay? Capital sigma. Is that clear? So our neural network will take as input the state and the action, whatever you see here, and will predict what? The mean vector and the covariance matrix of this Gaussian distribution, and you will sample from that Gaussian distribution to get to actually get samples for your next state. Is this clear? Okay. So this is just maximum likelihood using a multivariate Gaussian distribution, okay? So one thing you need to take care when you parameterize the covariance matrix is that your variances need to be positive. So how do we do that? Well, so this is the function that they use. So they use soft plus. Usually we can put any layer you like, and if you exponentiate it, then you'll always have something that is positive. Okay, so now let's go to the important uncertainty, which is epistemic uncertainty, all right? Uncertainty simply because we don't have training data in a particular regime of the system. And now you may say, why? Why don't I just collect those data? Well, because the reason you don't have this data is because your policy actually cannot execute the task. If what you care is how you pick up and down the object and your policy doesn't know how to do that yet, clearly you're not going to have data in that regime of the system. So here is how things look like here. From some states and actions, I have data, and you see there the red dots. So I have a lot of data around here, and I have a lot of data around there. And in some parts of the input, which is the combination of states and actions, I do not have any data, which is here, and in the beginning, and in the end, okay? And here I'm going to fit my neural network, and clearly what you see is where I have data, then my predictions are very close to ground truth. The black is the ground truth curve, and green is my prediction. And where I don't have data, actually my prediction deviates quite a bit from ground truth. Is that clear? Okay. So this is what's going to happen if you fit a deterministic neural network, where the output is not the parameterization of a Gaussian distribution for the next state, but rather is the elements of the next state directly. And now my question for you is, how would things look like if instead of fitting a deterministic neural network, I was fitting the neural network that I saw in the previous slide, where we parameterize the mean and the covariance matrix? What do you think? Would this problem be mitigated? The fact that, far away from the data, I don't have accurate predictions. What do you guys think? How things are going to look like in that case? Yes.
Maybe the line is thicker in areas where there's no data.
The line is thicker.
Well, some way of representing uncertainty. I'm not sure how much.
Very nice.
It would make the predictions better, but it would have some representation to the system of, how much it can trust.
Great. So now your colleague is saying, where I have data, I expect, the uncertainty, the variance to be low, and where I do not, I expect the variance to be high. This is what he's saying. And do you want to tell us also about the mean vector? What you expect the mean vector to happen?
I feel like the mean vector might stay the same.
The mean vector might stay the same. Okay, so let's see. So just to be clear, where we don't have data, there's still a unique answer, For S prime, it's just we don't know it. And what you see as the black curve is precisely we have a deterministic system in this case. Okay, but let's see what your colleague said. So he said the shade, like the variance is going to be higher where we don't have data, which is true. Yeah, and the mean is going to stay the same, right? The mean is going to stay the same. That's right, which is, I would say, unsatisfactory, because I mean, I just don't see here being extremely informative. In fact, look at what the range is. The range is all below the ground truth state of the system. It's not like centered around the ground truth state, right? Okay, it tells you, oh, I think between there and there is your prediction. I would say that's pretty wrong. Do you agree? And whether it is fatter than where we have data, sure, it is fatter. But still, it's pretty inaccurate. It's just not centered around the ground truth. Okay. So predicting a distribution will not help, because the means and variance of these distributions are similarly going to be inaccurate in the place where you don't have data. I mean, it's good that they're fat, but God knows how fat they are, right? How fat the variances are going to be. Yeah. So what can we do? How can I represent my uncertainty about my predictions? Does anybody want to give us a, let's say, baseline solution that we can do to represent our epistemic uncertainty? Something that, you know, he knows from some other courses. Actually, I even mentioned it earlier. Yes? Ensembles over neural networks, right? This is a very baseline approach of representing epistemic uncertainty with deep networks is just to train multiple networks. Okay, that's all. So, well, this starts from Bayesian inference that says the probability of a hypothesis given the data is the probability of the hypothesis, the probability of data given the hypothesis divided by the total probability. And what are the hypotheses here? The hypotheses are weights over our function, weights over our dynamics model. And so far, our model has been, we form a point estimate, right? For every synapses in our network, we only provide one single number. The principal way to do that is to have a distribution over those weights. We'll have some prior, then data will come, and then we'll have a posterior. This means that we have a distribution over neural networks, and sampling from the distribution would give us different instantiations of neural nets, which hopefully all of them would agree on where we have the data, and all of them would disagree where we don't have the data. And by looking at their entropy of their predictions, we'll be able to say, oh, here I really don't know what's going on. I have very high entropy. Here I have really low entropy. This is what we want. We want to know when we do not know. Okay. And a regressor or even parameterizing Gaussian distribution network doesn't give us this information. Is that clear? Such a network does not know what it knows and what it doesn't know. Okay. It just always predicts something. It says, oh, here's your mean. Oh, here is your variance. You fit in something crazy, still variance. Okay. Yes. The point is to keep around all the hypotheses, all the neural network weight hypotheses that fit our data, and not to overcommit. If you keep around all the hypotheses, then you can model your uncertainty. Now, unfortunately, such Bayesian networks are pretty, let's say, cumbersome to train. I mean, there has been some pretty great papers, and that, for example, they propose to make the distribution of each weight. Each weight means that each synapse, the bias at every single weight as a mixture of Gaussians, specifically mixture of two Gaussians. A very nice paper. I think I linked it from the website, or I have it in the, here, or I'm going to add it if I don't have it. And you see that every single synapse is now a distribution. Okay, multimodal distribution, two peaks, if we follow that paper. Now, unfortunately, this has not actually, let's say, I mean, I haven't seen it a lot in papers. However, what does happen is this approximation of Bayesian neural networks through. And how do we train ensembles? We take our training data, we instantiate a bunch with different initializations, and we train each one on different subsets of the data. Okay, so we make sure that they're trained on separate subsets. Is that clear? So here, what I show is three neural networks, an ensemble of three members: the blue, the green, and the purple member. And what you see here is that during close to the data, they all kind of agree, and far away from the data, each one disagrees. Do you see how well they agree? So their variances agrees. They agree on the fatness, and they agree on the mean. That's pretty low entropy here. They fall on top of one another, and they're pretty high entropy here and here and here. And by looking at this entropy, I can say I'm not going to trust my model in that part of the state space. Yes?
Would it make sense to have the ensemble networks have different architectures? Because isn't it possible that they would have the same answer that is incorrect, maybe away from the data, so they would all agree incorrectly somewhere else because they all have the same inductive biases?
A very good question. Yes, sure, you can do that, but they have different initializations, so usually they land in different answers far away from the data.
Okay.
But you can do that. You can put different number of layers and so on.
Cool.
Yeah, I haven't seen it anywhere, to be honest, but I would imagine that I think it's an interesting thing to try.
All right.
Okay. Yeah, so it's a good approximation to Bayesian networks that people use. So instead of having explicit posterior distributions for every weight in your neural network, you just have a set of ensembles. So you have like a small number of different predictions, and you look at their entropy, low entropy when they agree close to the data, and high entropy otherwise. So there's also this beautiful paper here, if you want to read it, HyperGAN, a generative model of diverse performance neural networks that essentially trains a model that cheaply, once you train it, you can cheaply sample multiple networks as opposed to having 3 or 5 and so on ensembles, so you can sample multiple of them. So let's assume now that we trained an ensemble of dynamics models from tuples of state, action, next state. Do not forget, guys, that training this dynamics model is a very, very simple supervised learning problem of the next state prediction. We just try to maximize the likelihood of the next states given current states and actions. Very, very simple, okay? And imagine that we took our tuples that the policy collected and we trained our ensembles, and we are ready now to estimate actions by unrolling, by look ahead, okay? Okay, so how would that look ahead look like? A colleague came on Monday and said, are we going to see estimation of actions through backpropagation of the model, in case that model, I mean, now that we have a dynamics model, we can all backpropagate. This dynamics model is a differentiable function. And the answer is yes, we will see these cases next week. Overall, when you have a dynamics model and you're trying to infer actions, this is a general optimization problem. You can do backpropagation, as we said last lecture. Today's lecture, we will see this paper does a very simple evolutionary search, cross-entropy method. And once we're done with this paper, we're going to go to AlphaGo, which does optimization through Monte Carlo research. You see? So different people optimize in different ways. Once you have a dynamics, how do you do that? Look ahead to infer, given the dynamics knowledge that you have, what is the best actions to apply given your current state. Is that clear? So we'll see a lot of different ways of optimizing over your model to infer actions. This is extremely simple optimization because you've seen it before. Okay, so what you do is you hypothesize a set of actions, you feed it in your network, the same actions. Let's say you come up with some set of actions, all right? You fit them in your ensemble, and as you see, every member of the ensemble sends you in a different final location, okay? Then you look at what happens after your temporal horizon capital T. This is the number of steps that you use in your unrolling, and now you are ready to evaluate how close that sequence of actions brought you to your goal. What is your goal? Your goal is just a state where you want to be. For example, I want my gripper to be in this particular configuration of the workspace. Okay? So you evaluate that. And if you have one neural network, then you will evaluate based on a single model. And if you have multiple neural networks, then you see that you have different threads, one per ensemble, and then you average essentially, and then essentially you average, your reward is the average of what different ensembles say. So you don't pick the one that brings you close to the goal because it may be wrong, right? It may be close to the data. You just average their predictions. Is this clear? The prediction is how close that S capital T is to your G, your goal representation. Yes.
Yeah, I have a question. So where does the action comes? Because in this case, the model is a dynamic model that models the next state.
Exactly, great. Where do the actions come from? Where do these actions that we feed into those unrolling came from, guys?
We have some external model free method, a policy that is predicting actions.
A very good question. So do we have a policy that is predicting actions? Let's keep this question for the next slide, which is this. Okay. So this is probabilistic ensembles trajectory sampling, PETS. This is how it works. We have, first of all, we do some random actions and we collect a set of experience. We use it to train probabilistic ensemble dynamics model exactly the way we just described. Each ensemble is trained different sets of the data, and each ensemble parameterizes a multivariate Gaussian distribution, its mean vector and covariance matrix. Okay. Then what do? Till task horizon, this is the number of unrolling steps. I use the cross entropy method to select actions by unrolling the model forward. So here is where actions come from sampling. I just sample crazy action sequences, feed them into my model, look at the fitness, okay, which action sequence brought me closer to the goal. This fitness is computed by averaging the predictions of the ensemble, okay. Each model of the ensemble tells me, oh, you are 1 meter from the goal, you are half a meter from the goal, you are 10 meters from the goal, and so on. So you average, this gives you the fitness, and then you keep resampling. You say, oh, this action sequence actually seems to bring me closer to the goal. Let me sample more action sequence around there. This is precisely the description of the cross entropy method that we discussed in a revolutionary search lecture, which I think also you need to implement it in your homework 3. Is that clear? Is this crystal clear? Okay, now you asked a fantastic question. You said, is there a policy? And the answer is yes. In many methods, jointly with this process, you'll be sampling a policy. Why? Because if you don't have a policy, this search over actions is nuts, right? You need a lot of searching if you always start from random action sequences, while your policy is going to have a very strong prior of, oh, last time I thought in this state, these actions are better. Now, of course, you don't want to be misled by your action policy, and you do need to explore. So I would sample some actions from your policy, some apples randomly, and so on, to make that optimization actually work, right? Because it's just an optimization problem. We have the dynamics model. We have ensembles. We know some parts of the state space or state and action space is, reliable, and in some other parts is not. And my goal is to find the sequence of actions that maximize my reward. And my reward here is closeness to the goal. The closer to a goal state I am, the higher my reward. How do we measure closeness to a goal specifically? So if I give you a goal representation in terms of a bunch of numbers, you just state in your state space how you'll evaluate your closeness to the goal.
Euclidean distance.
Okay, great. Euclidean distance, just L2 distance between whom and whom? Between whom and whom?
Is ST plus 3?
Yeah, the state that mentally you reached at your temporal horizon by enrolling your model, that's it. Guys, do you agree? Is that clear? And every model of the ensemble, as you see, will lead you to a different mental future state, which with a different closeness to goal, which means different reward, and you'll average those. That's it. This is homework 4. Question, yes.
I see there's like a YouTube link. I'm just curious what's the video.
Yes, so this is for you to click. I think it just shows this particular paper. It has a little video of the particular paper. Okay. Yeah. But I think it's pretty straightforward, so we don't need to. Okay. Yes.
So we sampled these action sequences according to like a soft policy with some randomness. Is that because going fully random, although it would give you like a more accurate, unbiased representation of the dynamics, is too hard?
Yes. So let me tell you, this is the first paper that used such probabilistic dynamics model, probabilistic ensembles. And in this particular paper, there's no policy. Okay. You always start from scratch. Clearly, of course, you can take let's all try to come up with the obvious extension of this. After my optimization, so I have my planner here. My planner is not like Monte Carlo research that we saw early in the lectures. That Monte Carlo research, first of all, was using a ground truth model, not a learned model. And it was not just trajectory sampling, it was very methodic Monte Carlo research type of sampling. But still, both of them are a planner. One is learned, one is not, okay? And they give you golden actions for a specific sequence of states. Do you agree? So they tell you from this state to reach to the goal, you need to do that. From another state, again, you need to start unrolling trajectories and you'll get another golden action. Now you can take those state action pairs that your planner gave you and train a policy with supervised learning. That's fine. And then use that policy next time to sample. You can make that policy an ensemble if you want, so that you know uncertainty of your policy. So for states that you know that your policy knows, you can use your policy. We have low entropy. For states that doesn't know, then you can just sample some actions randomly, exactly what this method does. So basically, training an extra policy will always be part, and we'll see some instantiations of this later. Is that clear? This particular paper, there is no policy theta that it always trains from scratch to optimize trajectories. And how it's evaluated? Well, it's evaluated using a golden specific initial state S. Okay, so you don't need the general state and action mapping because you always have the same initial state. Okay, is that clear? And your goal is, okay, given this particular state, what is the sequence of actions that will bring to this goal? So each time I ask you this, then you will do optimization over your dynamics model using cross-entropy method, and you'll give me the answer. Is that clear, guys? Any questions? Okay. Okay, so here they say that you optimize. So who can recognize what we're doing here? We're in a particular state. We do optimization. We, through this cross-entropy method, through trajectory unrolling, okay, we have a sequence of actions. And instead of just going ahead and executing all of them in our environment, what we do is we execute only the first one, okay? And then we go back and again re-optimize, and again re-optimize, and again re-optimize. This is precisely what we called in the last lecture model predictive control. You're in a particular golden root state. You have a specific goal state you want to reach. You do your trajectory sampling and cross-entropy methods to estimate golden set of actions. Instead of just closing your eyes and just let me execute them now and see where I reached, because you know that model errors accumulate over time, what you do is you execute the first action, you wake up, you see your next state, and then you repeat the cross-entropy method with a shorter now temporal horizon. Is this 100% clear, or any questions? Does anybody want to repeat for us what is a cross-entropy method? Because I know that you may not remember it because the homework 3 just got released. So you have not had the opportunity to, code it up, let's say. Any attempt, it doesn't need to be correct. Is the evolutionary search method, right? Okay. And how does it work? Okay, yes.
If I remember correctly,
yeah.
You have a whole bunch of different predictors that you test, and then they all do they have a certain performance at predicting. And then you do a weighted average to get your next best predictor by sort of weighting each predictor by how well it did.
I see, yes. And the truth is that during our evolutionary search lecture, we use this method, cross-entropy method, to sample what? Do you remember what we were sampling, guys? What we were searching over? Here we're searching over actions. Policies, which is what exactly? How parameters of the policies, right? And we said that this is trivial when the parameters of the policies are small, okay? So it's not a neural network with thousands of parameters, it's just some linear policy and so on. And we said, yes, this is very easy. And we showed a very cool 2017 paper of how to do similar evolutionary search with really high dimensional policies, correct? So we were sampling parameters. That's absolutely correct. And we were, one search we said is that there is a Gaussian distribution over those parameter space. But if this confuses you, just think about a grid search. You just sample a bunch of parameters or policies, you evaluate them, so you compute the fitness of each one, and the parameters of policies that gave you highest fitness are used to perturb for the next generation, right? So low performing policies, you cut them away. They're not part of the elites. You threshold based on the fitness, you keep the best performance, and you do what to them? You mutate them. You change arbitrarily their parameters. Now, the mutation we discussed there is that you have this Gaussian and you sample from Gaussian. Well, it doesn't need to be like this. Now, the difference with that lecture where we were sampling policy parameters is that here we're sampling what? Instead. So who would like to say what we were sampling in our search here? Actually here. It says we use the cross entropy method to select actions by unrolling the model. What are we sampling over? Some suggestions?
Trajectory.
We sample trajectories, but how do you sample trajectories?
By unrolling the dynamic model.
We're borrowing dynamics model, but dynamics model takes as input a state and an action. And I give you the initial state. So what do you need to fit to that dynamics model? The what?
Actions, right?
The actions. So what we're sampling is actions over a time horizon. So our unknown is a vector that has the action parameters for every time step. That's what we're searching over here. It's not policy parameters, it's action parameters for every time step. Is that clear? This is what we're sampling. Okay? So you sample, say, okay, what about these 5 actions? If your horizon is 5, you fit them in your dynamics model, and then the best performer such action vectors are kept for the next generation of search by perturbing them and so on. Is that clear?
Question.
Yes, please.
So what does the action parameters by having?
What does it mean, action parameters?
Yeah, is that cross-entropy method?
I didn't understand that question. But if you think about an autonomous vehicle, the actions would be how much shall I press the brake or the gas, and how much shall I steer, like what should be my steering angle, these 2 numbers. So I have 2 numbers. If I have 10 time steps, I have 20 numbers. This is what I'm searching over. This is what I'm sampling. This is what I'm optimizing over, which is what? How much to press the gas and how much to steer for the next 10 time steps. Is that clear? This is what we're optimizing into our evolutionary search. Much like before, we were optimizing over the 50 parameters of our neural network. Yes?
We're going to learn from T1 to fast horizon. We're going to learn a better set of actions to take for this particular goal.
Yeah, we're optimizing over them. We're searching over them. Yes.
So the next time we try to run this, we'll have to start from random.
Unfortunately, in this paper, yes. But now I'm going to show some other papers where you distill the good actions into a policy, and then you can sample from your policy. So next time, you don't start randomly again. You start by sampling in your policy or something. Okay. Yes?
So in PETS, in this version, we're not updating the dynamics model as we get more information. We're just training the dynamics model right at the beginning.
Okay.
Okay. We do update it. Okay.
1 second. Wait, 1 second. No, I'm not sure. 1 second. Do I have it here?
Step 3. We are updating the dynamics model.
Well, you're right. This is a buggy prediction. This training should happen here. We constantly retrain the model. Wait a second. Yes, so this is wrong. So this pseudocode is wrong. That's a great point. So basically, what you need to do is here, you go to 1. You train again. So basically, instead of saying go to 2, you need to go to 1. Okay, is that clear? So the D environment keeps growing. Okay, you do multiple CEMs, multiple optimizations, 1 for every time step in your horizon. simply because you decide to do model predictive control. If you don't want to do model predictive control and we just to execute all the actions, that's fine. It's just unfortunately, you probably the last actions will be nuts, right? Because of the model error compounding over time. And then instead of, you don't go back to 2, of course, now you have more environment extractions, you go and you update your model and repeat. Is that clear? Great point. We always update the dynamics model as we get more environment interactions, right? Because otherwise we cannot improve our searches. We're stuck, right? Why would we redo CEM afterwards? If the dynamics model is the same, probably we're going to land exactly on the same actions.
Okay. And here it doesn't specify how we train the dynamics model. It could be by CEM or it could be by a different way of training it.
Great. So now I really want you to answer this question of your colleague. By the way, guys, let me be super clear here. The second part of the course is super difficult. I really do not want you to postpone your reading because you are not going to enjoy the lectures. We're not going to be able to communicate. I mean, the first part was kind of okayish. Now the second part, I think is super hard. You really need to read. Now this is just one paper, but it's very important. It has lots of different concepts that you can try. So you read it, you discuss it with your colleagues, you come on the office hours and so on. You ask questions because now look how silent you are because you don't even ask the questions, right? So the more you ask questions, the more you get it, the less you need to study. So it's super important that you don't wait for quiz 2, let alone quiz 2 is coming up soon, I think. 11th of November. And that's pretty clear, close by, right? I wouldn't wait. So I really wouldn't wait. So your colleague asked the question and he asked, this pseudocode does not specify how we train the dynamics model, he says. Are we going to train it with CEM or with something else? Is this what you asked?
Yes, that's what I asked.
Oh, sorry. Okay. This is what you asked. Who would like to answer this question?
I think it's just supervised learning, right? You regress to the next state and reward. If you are predicting.
Okay, so here we don't have reward simply because in robotics tasks often is all about reaching a goal. So that's why we just have the next state function. But this is also fantastic, just to be clear about the reward. So he says there is no reason to do non-gradient based optimization here, right? I mean, this is a super simple supervised learning problem. You have tuples of the form state action next state. You just train your model. And he said, oh, you regress. But just before we said, we don't regress to the next state. We actually, regress to the mean vector and to covariance matrix, but that's fine. Okay, essentially you do maximum likelihood and the multivariate Gaussian distribution. That's it. Okay, and if the covariance matrix, you throw it away and you only want to parameterize the mean vector, then you just have least squares and that's it. Okay. Is this clear? So the dynamics model is trivial. You just train it with your data supervised. Okay. Now you may say, why don't I chain my dynamics models and backpropagate all the way to search with actions, not in an evolutionary search manner, but with a differentiable manner, right? We'll see this thing next week. We'll see this thing next week. Now we have dynamics, right? We have differentiable functions take us from S0 all the way to S capital T, S task horizon. Capital T is the task horizon, right? So you may, your error is what? S capital T, where you landed to be close to G. So you put there your L2, you backpropagate all the way to the actions. Okay. Now, unfortunately, this is yes. So because it's a gradient sent through very few parameters, which are the actions, is not like neural network parameters. Okay. Then you have all this getting stuck in local optima problems. So that's why we don't do. We say, let's do cross entropy method. The way gradient descent works so super well on neural networks because you optimize over so many parameters, right? There is this over parameterization. Otherwise, in standard problems, when you gradient descent, you get stuck. It's not a convex problem. Okay. Is that clear a little bit or? Okay. Very good question. Very good question. This is very important to ask this question. Are there any other questions here? A very good point of the buggy code here is we need to retrain the dynamics. This is all fantastic points. In any case, here's the conclusion. PPO, soft actor critic, what else we know? DDPG we've seen, some Gaussian process stuff. And it turns out that the blue thing does really well. And this now say, okay, it does well. Well, when this paper came out, that was a very big deal because as I told you, asymptotically, the model-based methods were always underperforming the model-free methods, correct? Okay, so let's summarize what we've learned. We said that training a model is a supervised learning problem. We just do maximum likelihood. And when I have a model, I need to optimize over actions. And there are multiple ways to do this optimization. And we just use the cross-entropy method. The third important thing we said is what your colleague said. We iterate. We train the model, optimize over actions, deploy the policy, all right, get new interactions, re-update our dynamics model, optimize over actions, and so on. That's all. These are the three things that we'll see again and again. All right. So now here is a couple of other papers, simply to see that, there are tons of papers out there. You don't need to worry about them. Some of them are optional readings. I mean, maybe all of them are optional. So I don't think we're going to have any quiz questions here. But the answer, you guys asked really good questions. You said, where is the policy? So now you'll see there's a policy here. So let's see. So here's the policy. It says it in we start. We have a policy and we have some environment interactions. So we run this policy to get some experience sample. Before there was no policy, we're just doing random actions, okay? I mean, here also they're going to be random because we initialized our network randomly. And then what we're going to do, here is our ensemble. We have lots of members of the ensemble, same as before. Again, our state is low dimensional, similar benchmarks as the previous thing with the cheetah and so on. And here's what we're going to do. Now, we are going to collect simulated experience from the model, all right? We're going to sample from the model starting from a golden state S0, and then we'll be updating our policy using TRPO, which, if you remember, is exactly like policy gradients plus some taking care of how much to be the step size. The step size not be too large, if you remember. We look at the KLs of the action distributions per state, not the action. This probability distribution of action should not change too much from iteration to iteration. Okay, that's it. So what you see here, and how much do you update until the performance across all models of the ensemble stops improving? Okay. Wait a second now. I think this 4 needs to be here. Repeat until, oh yeah, it's there. It's fine, no problem. So here you see something really different. Instead of starting from random actions, we have a policy. Okay, so instead now of optimizing over explicit action coordinates per time step, we're going to optimize over policy parameters. Okay, and guess what? One such optimization, we said that on Monday, is like use your model, query it, sample tons of synthetic experience, mental experience. You just sit there and think, what will happen to the world, and so on. And you use that simulate experience much like you use real experience when we had model-free methods to update your policy parameters. Here's another optimization. So you can do all crazy optimizations you like over what? Over your actions or your parameters of your policy, as you see here. Yes?
We can still add in a step saying like update your dynamic model, right? After.
1 second. So go to 1. Yeah, it was not done. Absolutely. Of course, we always did it. This will always be there, just to be clear. Otherwise, we said why this doesn't work, because then we have this distribution mismatch. The data the training models were trained on and the data the policy visits at the deployment, they don't match. And so the dynamics model is not accurate and so on. So we will always be iterating between updating our model and updating our policy. And the reason I'm going through these papers is just to see that all of this model-based RL is variations of this theme of training a dynamics model and optimizing our policy over it. Okay? And here we have this very simple, again, non-differentiable optimization, but by using model-free reinforcement learning. Okay. Okay, so where does this ensemble play a role here? Is the following. You keep updating the parameters, and each time you update the parameters of your policy, you look how well you're doing according to all the members of the ensemble. Okay, and as you see here, guys, we also have rewards. Do you see? So you measure your reward across all the numbers. So if you have, let's say, 5 members of the ensemble, you are not going to keep taking gradients if in one of those models thinks that your reward is going down. Does this make sense? Yes.
Will the model, dynamic model, also predict the reward instead of only the next state?
Yes, here is exactly where it says. Yes, it's very important. S prime, R prime. Yeah, the reward of the next state. Okay? So you fit your policy into models collected from different ensembles. You deploy your policy there, and you want to make sure rewards are going up on these trajectories. Correct? If one of the models says, oh, rewards going down, then you say, okay, I stop doing gradient descent. I'm not going to optimize anymore. Do you see? So if you want to know, because this is the most important thing, right? Otherwise, I can throw away the ensembles. The whole point here is the ensembles that capture model uncertainty. And I'm saying the way things are handled, you have your ensembles. The importance is in the until statement. Performance across all models of the ensemble stops improving. Yeah, I think maybe what I wanted to say is in performance across some model of the ensemble stops improving, or some. So I'll fix this one. So here is another version now, again from another Sudoku from another paper. The problem is the following: long rollouts unfortunately have lots of error. They accumulate error because you feed your prediction back as input, and in the previous Sudoku code, that's why I put it in red. You always start from S0 here. You see starting from S0. Now the next paper will do this groundbreaking step of not starting from S0 here. Sample some state from your experience buffer and start from that state. In this way, the task horizon and your model rollout horizon don't need to match because you used your model to help you do well from the middle of the task until the end. Okay? So you can use actually very short rollouts. This paper said that even single step rollout or two step rollouts were actually useful. Okay, so let's see the pseudocode all together. Yeah, so the model rollout can be shorter than the task horizon. And yeah, so let's see what's going to happen. So again, there is a policy here. So this is good, is exactly what you were saying. We run the policy, we collect experience. Again, we're going to train an ensemble with supervised learning. And each ensemble is trained on different subset of the data. And then for a bunch of model rollouts, you get the state from your experience buffer and then collect again simulated experience. And then you use soft actor critic instead of TRPO. You grab your favorite model-free method, then you use your simulated experience on. Okay, and here is my question for you. Yes, why don't you ask your question first?
So I guess I don't really understand how the uncertainty of the ensemble plays into the policy training. So like if you sample your experience buffer, you go through some trajectory and you get like 10 very different things. Should that update the policy differently than if you get the dynamics of all of the 10 ensemble models if it is the same thing?
Yeah, so what I have understood by reading those is the following. You keep updating, and as you update your parameters, you land on different policies, right? So you deploy those policies on this experience of different ensembles, and you see how your mean average reward goes. If your average reward starts, for one of those members starts going down, then you stop your updates. Do you see? Because this means that you land on policy parameters that one of the modes of the ensemble seems that is not helpful, right? So you want to make sure that you keep update your parameters as long as all models tell you, yes, you're going in the right direction. Because you hope that because they all agree, it means that, they essentially have seen those data, right? They are certain.
It's kind of like a floor condition where you would stop going that direction if any of the...
Yes. I can add some more comments to make this explicit because this is precisely the important part, right? This averaging across models or taking all models into account as opposed to, one of them or not taking them at all into account once you collect the data, etc. Okay. Okay. Another obvious thing that happens is because this simulated experience is collected under multiple models, right? So some of this simulated experience can be in contradiction to one another. Under one model, that state and action send you there. Under another model, it sends you there. Instead, you're in a different place. You see, we sample from the model K time steps while using policy to use the exactly. So this contradictory essentially experience, if you use it to update your model, hopefully will balance out and it will not land you to crazy places. Is that clear? Because you sample synthetic experience from multiple models, so in the states and actions, they all agree that they have high rewards. They're going to use to reinforce your policy. For those where things are contradictory, probably, hopefully the policy is not going to go crazy. It's not going to take steps. Does this make sense? Okay. But great question. Very, very good question. Yes.
Just want to make sure like you have that sample of like multiple dynamic models, but you only have one policy.
You have one policy. Yes.
So you sample from N models and then put N examples into your experience buffer. So for each step you put N examples into the experience buffer and you do this like N process.
Yes, good question. So I think all one trajectory is sampled from one ensemble, and then you sample another whole trajectory from another ensemble. You don't switch ensembles at every time step. Okay, does this make sense? So you grab one guy, you collect the whole trajectory. You grab another guy, get another trajectory, and so on and so forth. Is that clear?
So you random select a dynamic model.
Yeah, an ensemble. Yeah, a model about from the ensemble exactly. Okay, so when you collect this D model, you sample all of those guys, all of the dynamics models. All right, but I think you use one per trajectory unrolling. Is that clear? Okay, great questions. Okay, so these different pseudocodes are just to show you the trend, I suppose, the natural sequence of steps that all methods will follow, okay, for model-based reinforcement learning. Oh, wait a second. Here I say exactly the opposite. Well, here it says exactly the opposite. Based on your question, it says that different transitions along a single model rollout, a rollout is a trajectory, are sampled from different dynamics models. Let me clarify this because I'm not 100% sure. I haven't read that paper recently. Okay, but these are design choices. So this is very important. Okay. So yes, so they show again that things are looking good. And that's all I wanted to show you from this model based on low state space. Okay. Do you have any? You had some pretty wonderful questions, so this is really great. Any more? Yeah.
So what is the format of the simulated experience? Is a simulated trajectory? So if it is a trajectory, do I need to decorrelate them in order to learn from them?
Great. So the question is, what is the format of the simulated experience? What exactly simulated experience means? Is it just a sequence of state action rewards? And if I have such experience to learn from it, do I need to decorrelate it and so on? Any answers? Yes.
Yeah, you can just throw it into an experience buffer and then sample randomly to decorrelate it.
Exactly. So we do exactly what we do with real experience. Exactly. So why simulated experience is preferred over real experience? Because you can just query it without interacting with the environment. Super, super cheap. Okay, you don't need to interact. You just sit and think, basically. Other questions? All right, great. So now we're going to do something else. We're going to, again, model-based reinforcement learning, but the model is going to be known, okay? It's going to be known. Next week, for the same domain, we'll discuss learned models, but this is more advanced. So first, we're going to start next week with learning models from images. We'll see different formats and so on and so on. And we're going to see, dynamics models on a latent space. And eventually, we're going to go back to alpha to go and see, okay, Monte Carlo research on a learned model, mu0. But this is at the very, very end. So this is also your homework 5. So now we're going to start very simple. And we're going to say the model is given. And to be honest, in all those games, we know the model, which is in that simulated environment. Of course, if you take that black piece and you put it from 2,2 to 3,3, and well, the next state is, the same board configuration with the black piece at 3,3. Okay, I mean, clearly. So let's see. Just to refresh your memory, online planning with search, we were in a particular state as 0, and then we built a full search tree on the current state of the agent as the root. We want to select the MoveX and execute it and so on. We said that unfortunately that for many games as well as for the real world, the state space is enormous. So that sub MDP is also huge. So what do we do when, exhaustively enumerating states is impossible? We sample. And in fact, that's precisely what we did in the, few slides ago in the previous slide deck, right? We were sampling trajectories, if you remember. We didn't do exhaustive search to find actions, given our learned model. That's fine. Now, so exhaustive search is hopeless. Okay, we cannot build a whole search tree under a particular root node. So planning is thinking before acting. Imagining all possible futures, all possible trajectories is too costly. So instead, Monte Carlo tree search will select few of them. Now, the trajectory sampling we did does exactly the same thing. It also selects a few of them. Now, Monte Carlo tree search is a more methodic way of imagining the future than just sampling independent trajectories. Is that clear? It's just a more methodic way of searching over the future, as opposed to sampling independent trajectories. That's all. There's nothing more. So we will come back to that question of when is Monte Carlo tree search helpful over just trajectory sampling and so on and so forth, okay? So if you remember, the main theme of Monte Carlo tree search is instead of just sampling trajectories, okay, which is exactly what we just did. So Monte Carlo search is exactly what we did a few slides ago. You just sample trajectories independently. Monte Carlo search improves upon it by learning to select better actions. Okay, the more it samples trajectories, that's what it does. And if you remember, there was, 4 phases. One was, there was something we call in-tree policy, where we select actions based on the UCB criterion. Once we visit a new node, we just add it to the tree. Then after that, we were, if you remember, playing randomly. Then we would see the reward, or would truncate at some point in our trajectory and take some rewards, and then backpropagate and update the values of all the nodes that we have visited. And visually, things look like that. Dark black dot here is the root state. Here is within the policy where we use the UCB criterion that balances exploitation, exploration, if you remember, the Q estimate for that action versus how many times we have played it. And then we go outside, then we run sample randomly, then we get the reward, and we backpropagate to the nodes and so on. And if you remember, we said that Monte Carlo tree search, the way we described it, is as if you go to play chess and you just show up and you trust your GPUs being huge, and you're going to search online if you've never trained before the game, right? You never played before the game. You go with no prior knowledge. Is this clear? Did you see anywhere in this Monte Carlo tree search process that we just refreshed in our memories us using prior knowledge before you start playing the game? Okay, now imagine that I want to go to the chess and I have less GPUs, and I cannot do this homongoous Monte Carlo tree search each time I select an action. How do you think? Does anybody want to, suggest a random baseline, something random, where imagine that I played at home, and when you play at home, what can you do? Well, in our reinforcement learning course, we said 2 things you can do. You can learn a policy that, given different states, tells you, these actions are better than others. And I think one of you suggested right earlier, why don't we learn a policy so that we don't start from scratch each time in our cross-entropy method, right? So this is supernatural. Another thing we discussed a lot in our earlier part of the course is about value functions. This state is good, this state is bad. So now my question here is, can I spend time at home computing value functions and policies, so when I show up to play with my, chess master, I'm better prepared and I have better chances during my Monte Carlo search to beat him or her? This is what we're saying here. Can we do better? Is this clear? Okay, great. Now, if I give you a policy and a value function, you just randomly suggest something. Where would you put it in our Monte Carlo tree search procedure that we just saw? So now you have a policy, right, that gives you some prior of how to select actions. Monte Carlo tree search uses action selection based on the Q, which, by the way, the Q at the beginning is random. I don't know if that was clear, but it starts super random, plus some exploration bonus. I say we put our policy there during action selection. This is natural thing to do, correct? Another natural thing to do is after the tree, not to play randomly, but to put some policy there to play. correct? Because now we're playing randomly. And another last thing that I think is also makes sense is when you have a value function, instead of only trusting your reward, put also the value. Like you reach the leaf node, evaluate through your value network and get an idea how good or bad that leaf node is, and use that value to backpropagate. Does this make sense to you guys? Okay, so that's AlphaGo. This is the algorithm that DeepMind proposed. It's very complicated, has multiple steps. Not that difficult, is exactly what I just described, but it was extremely important because it beat the world champion in Go at that time, which was Lisa Doll, in 4 out of 5 games. Okay, in the big tournament. I don't know if you've seen videos of that. There is a pretty amazing, short like movie. We probably will upload. I think it's super inspirational, really great that you can watch. And now that you're going to know the algorithm. Okay, let's see. Can we inject prior knowledge into state and action values instead of initializing them randomly? Which states are good and which actions are good? That's what we're talking about. And the answer is yes. Yes, we can. So we're going to use neural networks. Okay, 2 neural networks, a value neural network and a policy neural network. The value neural network will be evaluating board configurations to tell us which is good and which is bad to help us prune the depth of the search. So if you reach a leaf node that clearly is bad, right, you can, bias your, right now, if you remember Monte Carlo research, once you reach a bad node, then you just play randomly and you get the final reward. This is extremely noisy evaluation of that state, all right? Many times a human can say, okay, this leaf node really looks crap. I mean, maybe your random policy, though the way it played randomly, it figured out that you're going to win from there. So clearly, this is super noisy. This is not the right thing to do. So if you have a value network that you've trained to tell you that I think the state is bad and so on, you should use it, okay, to bias your rewards. And the policy network that tells us which actions are good given states will help us to prune the breadth of the search. But the breadth has to do with the actions to try, and the depth has to do with states to visit, correct? Okay, so how we're going to do that? So here's how the value network looks like. It takes a board configuration and spits out a scalar value. Very simple. How good is that board configuration? That is the input, the output of the value network. What is the input and output of the policy network? Yes?
The board state just like this, and then a distribution of the actions.
A distribution of our actions. Exactly. And because we know the model, we know exactly what actions are legal and illegal. So we have a distribution of our legal actions per state, right? Because we know the model, we know legal and illegal action. So what does it mean to reduce the depth with the value network? It means that you go to the leaves and evaluate them, feed them into your value network and get some scalar values. And the prior network here is the policy network that tells you what are the most likely actions, and reducing the breadth. Okay, this means that you evaluate different actions. So instead of just trying all possible actions per state, what we did before, if you remember in UCB, to use UCB, you need to first try all possible actions. Okay, remember? And then you start using your UCB. I don't know whoever remembers that. Right now, you may not need to do that because you have your prior that tells you clearly some actions are not supposed to be tried. Okay, so let's see how we can do that. So AlphaGo has 4 ingredients. Let's see how they look like. First, we're going to trade 2 policies, a cheap and an expensive one. Second, we're going to trade a 3rd policy with reinforcement learning and self-play. The first 2 policies are trained supervised from human experts. Third, we're going to train a value network based on the reinforcement learning policy. And last, we're going to combine the policy and value networks in the Monte Carlo research process. And now you have 3 policies and you say, okay, which one I'm going to use? You're going to use the first 2 policies. The second policy here, in the second row, this policy, is only used to train the value network. And the value network is used in the Monte Carlo research. So let me say it one more time. We're going to use Monte Carlo research process. In this Monte Carlo research, we're going to have 2 policies. They're going to be used, an expensive one, which means a big network, and a cheap one, which is a shorter network. Why? The short network will be used outside of the tree because we're going to query it tons and tons and tons of times, while the one within the tree, we're going to, use it less times. Do you understand? Because there are multiple moves that you need to do outside of the tree. Okay, both of those policies will be trained supervised from Go experts. Okay, so we'll take a huge supervised data set of expert moves. We're going to do imitation learning, behavior cloning. That's it. And we're also going to use a value network. And that value network will train it by using policy gradients, something like, very simple like this. And the policy that we'll be using in that reinforcement learning is going to be this new one. This will be initialized from the supervised policies, but will be fine-tuned with self-play. And when you fine-tune with self-play, means that what? You'll be able to do better than the experts. Okay? So this value network now will be informed, will be computed from this policy that's actually better than the experts. So let's see each step in isolation. So this is the simplest possible step. It's just supervised learning. We'll predict expert moves. We'll randomly sample state and actions from expert games, and we'll predict the probability over the legal moves. That's all. Now it's a 13-layer policy network, 30 million positions, and so on and so forth. Okay. So even that policy network was able to do better than policy networks of other research groups because of its architecture and the huge amount of the training data set. Very simple. Okay. So now the supervised learning, that's the 13 policy, is the expensive one. There is a much shorter one, which is the cheap one. Now, second time, now comes the reinforcement learning. So we're going to start now doing self-play. My goal is to improve over my supervised learning policy. This is a typical thing we'll see many times in the course. You want to do better than the expert, you don't need to start with reinforcement learning. You just start from a supervised learning policy. Okay? This is what they did. Very makes a lot of sense that you initialize and you start fine-tuning to try to improve upon the experts. So I initialize my weights from the supervised learning policy, of course, from the expensive one, from the good one. Clearly, the cheap policy is going to be worse performance than the expensive, right? Now I'm going to just start playing against myself and with simple policy gradients like this one, as you see. And the way, so that's it. Actually, there's not going to even be an advantage function here. They use the reward directly. Okay. So this is standard policy, not actor critic methods. Okay. And the RL policy, this is good, won 80% of the times over the supervised learning policy. So I did manage to improve over my supervised learning policy. Do you guys agree? Yes.
So when it says weight initialization from the SL network,
yes,
saying that it like before it starts training, it's just copied from PC.
Yeah, yes, you copy the weights. All right, so you start being already great when you start.
And then for the games, just P-row against P-row.
Yes, against the same guy. Yeah, right. Sometimes you also play against previous versions of yourself. So as you're being updated, sometimes you add your opponent is not the same as you. It's also some previous versions of you because you need to be able to beat both yourself as well as, maybe less good experts. Imagine a baby comes and does some random movement. You're like, oh, I haven't seen this in my trainings. Do you see what I mean? So that's why sometimes you sample from previous. Now, here is how the simplest way to train a value network is. Yes, please.
Going back one slide. When we say like self-play and RL versus SL, this is all using those policies to inform Monte Carlo tree search.
Very, very good question. Very good question. And let me just clarify. There is no Monte Carlo research so far. You just play from your policy. Okay? In fact, yes, you just play from your policy. You don't feed them into a Monte Carlo research process. When it says we beat the other groups and so on, means that the actions were sampled directly from the policy network. Okay? This is a great question, though. In fact, when this paper came out, nobody had ever combined neural networks Monte Carlo research. Can you imagine? This was not even a thought. Yeah. Okay? So now it's going to come at test time. All right? So, but the great question, though. Okay, so now third line is trivial. Let me tell you what's the third line. You'll go do your self-play. You collect board configurations. You will see whether you won or not. You will pair board configurations with +1 or -1, whether you won or not. And then you'll train a regressor. That's it. Can you imagine? the simplest way to train a value network. You say, oh, it seems that from this configuration, I won. From this configuration, I lost, and so on. Now, here is the insane thing. They say that once you have a game, because the board configurations are very correlated, when you play a game of Go, apparently different trajectories of the game look different, but, different board configurations consecutively, they only differ from one piece. So from each game, they take only one sample. So if you want to do 50 million, training set to train your value network, you need to have 50 billion games. Can you imagine? So you sample one example per game to train your value network.
But what if they sample like two beginning of the game and the board has no pieces? Then it will be a bad example.
I didn't understand. No, actually, wait a second. This isn't. So the question is the following: what if they sample a state early in the game, when there is only one piece hanging there, and then you say, oh, from that initial piece, oh, you know what, I won, the white one. Okay. Then your colleague is asking, is this a bad example? Who would like to answer? Yes.
Just gives you some idea of early advantages, right?
Yeah, and probably in those early advantages, I would say, 50% times you won, 50% you lost. And so the network figures out that, okay, the value here is, around zero. Nobody is clearly, is not clearly beneficial for me and is not clearly negative for me. Do you agree?
Yeah.
Okay. So of course it's not a bad example. I want to know values of states both early on the network as well as late. The truth is that, though, correctly you're saying that late states are more informative, right? And that's precisely why we do Monte Carlo research. That's precisely why we look ahead. Because we know that if we just take the current state and evaluate, then action potentially is not informative. But if we think ahead and see what happens, then my value network will be able to say something more useful. Okay? Other question?
Just super easy. Is there other ties in Go?
Well, I have no clue about Go, but yes, there are. They also take care of this. They put, +1, -1, 0. Not only ties, but they also have some other configurations. So I won you by 2 or some. All of those show up on the reward. Now I just keep it simple, but yes, all of them reflect on the reward.
Okay. I guess I was kind of curious because if it's the pulse sequence itself, like if it's tic-tac-toe or something,
Yeah.
then it's always going to reach a tie. So I wasn't sure if there was that causes issue.
No, it's not. You don't need to reach a tie because your policy is stochastic, right? So you just sample. It's not a deterministic policy, right? Do you see?
Yeah.
So who knows what's going to happen? Okay. Other questions? Yes.
So you mentioned that they use the reward only at the end of the game.
Yes.
Won't this reward be too sparse for the
Super sparse, yes.
for the process of learning?
Yes, that's why you need to play a lot of games. Yeah, it's very sparse. I totally agree. They played millions and millions of games during this self-play. I really suggest you read the paper. It's a Nature paper to see the details. And you know what? I mean, in 5 slides, I'm going to show you a method that shines, that's super much simpler, uses Monte Carlo just as training time, but it's just for historic reasons that it's important to see the first paper to be able to appreciate the second paper. Do you see what I mean? Let alone that we refresh concepts of, okay, RL and how to be used and so on. All right? Okay, so let me move on. So that's how you train your value network. And here is the most important part. Now you train policies and you trained value networks and you are ready to combine them into a Monte Carlo 3-step process. Now here is the interesting part. At training time, there's no Monte Carlo research here. At training time happens the 1, 2, 3 dots that I just told you. You train with imitation learning, you do self-play, you train your value network, and that's it. And now you go to play with this lizard doll. And here's where Monte Carlo research enters. Now, the truth is they also did some Bayesian optimization for some hyperparameters of this Monte Carlo research. But let's not worry about how to. Okay. So let's discuss the obvious ways you can combine neural networks with our Monte Carlo research. Here is an obvious way. I say that when you're in tree, instead of just taking into account the Q, as well as the exploration bonus, which is NS divided by how many times you visit the parent state, and how many times you took that particular action from that state. I say you also multiply with your prior. What do you think about that? That's precisely what we said earlier. Okay? Is this 100% clear? Because we're going to see it a lot, this thing. So you have a queue. The queue is completely random when you start your Monte Carlo research. It starts from 0, right? And then you have your exploration bonus. And now you have this nice prior. And now because you have this p theta of alpha, you don't need to try every action before using the UCB. You forget about this now. Okay? So that's the most important thing. Here is the action selected at time step t from state st. The queue, you know what it is. The queue of the Monte Carlo search process from the back propagating the rewards that you get. P theta is the new thing, is our prior. And also you know what it is how many times you play in that state and action, and n of s how many times you've been to the state. Okay? So that's a very important change here. Do you agree? This happens within the network, and instead of using UCB, now you use the prior informed UCB. Is that clear? Yes.
Why do we not also inform the queue with our value function?
Because our value function is a value of states, not a value of states and actions. We're about to do that. We'll do that. Just hold. Great question. Just hold now in the next slide. Okay, so 1 second. So this is the only thing I want to say is that, so basically we use the supervised learning policy to give us those p theta of alphas. I mean, here we call it PS, alpha because the picture shows it as P, alpha. But basically, each time we reach a leaf state, we add it in the tree. We feed all actions into our policy network. We get our p theta alphas and we save them. And that's it. We don't feed them again and again. We just feed them once. We save them. Now we know the priors of those actions. And that's it. And now each time you add a new state in your tree, again, you feed all the actions in your policy with the corresponding state, get all the priors, save them, and that's it. So yes.
Why do we use the expert policy as our prior instead of the fine one?
Great question. So they say I had exactly the same question. They say in the paper that the expert policy that is trained with supervised learning is actually more multimodal. And you want to be able to, they say it's good. While the reinforcement learning one is more unimodal, it always uses the same action in a particular state. Great question. More diverse, yes. Now, of course, you may say, oh, but you have the exploration bonus. Well, sure, you have the exploration bonus, but it's good to also have your prior to be more diverse, okay? Okay, great. So we figure out how to use the prior, the policy. Let's see how we're going to use the value. Here it is. We're going to do exactly what your colleague said. We're going to use our value neural network to inform the queue. How we're going to do that, though? As we go and we are outside now of the tree, and we play, and we land somewhere, we do not, we land at the end of the game and so on. Actually, no. So we are here on the leaf node, right outside the tree. We play randomly from the chip policy. We get a reward at the end, whether we win or not. And now the value of that policy here is a weighted sum of the actual reward, Z, and the value, evaluating that leaf node. Do you see what I mean? Here is the node which just got added into my tree. Now I'm at the frontier of the tree and I'm about to start playing randomly. Instead of playing randomly, I'm going to use my chip policy. Now you know where the chip policy is used. I'm going to go at the end. Oh, well, I lost -1. But instead of assigning as the value of that state -1, I'm also going to do a weighted sum of -1 and what my value network thinks the state is. And I'm going to use this as the reward to back propagate to the queues. So indeed, we're going to use the value to update the queue. Okay? Yes? Okay, great. We evaluate the leaf node like this. This is the train value function. This is the reward from the fast rollout that is played at in the terminal step. You need to play all the way if you want to get a reward. Okay? And here is the back propagation. Look, this is exactly what you said. Okay, the queue of every state and action that I have taken is a weighted sum of all the trajectories that I've played from the state and action with the values of their terminal leaves. That's the back propagation. Before we were using only the rewards, whether I won or not at the end of the rollout. Now we use the value of the leaf, which is a weighted sum of whether I won or not, plus the evaluation of that leaf node from my value network. Is that clear? Any question here? And that's it. That's the end. And now you need to know, okay, I give you a budget. Let's say I give you simulation budget 2,000. If I give you simulation budget 2,000, how many nodes your tree is going to have? 2,000, because at every trajectory you add one node, if you remember, but don't worry, we'll see this in the next lecture, just to refresh. But basically the way Monte Carlo tree search works is that each trajectory you add one node. So if you have 3,000 trajectories, you have 3,000 nodes within your tree. And then at the root, when you're about to play now against your competitor, you'll choose the action that was most visited at the root node. That's it. Not UCB, but what was the most visited. Okay. That's it. It ended. Okay, this AlphaGo 0, we'll see it next week. This AlphaGo, and that's how it works. Please check the paper. Have a great week. See you on Friday for the recitation. Yes, and thank you for being here. No recitation. So see you on Monday then to do AlphaGo 0. Okay?